Hi, everybody. As we get started on the last topic that will be on the AP exam this year, I just want to remind you that if you have any questions about anything we've talked about here with gravity, please reach out to me via email. I am going to be scheduling some time later in the week, and you will see that in the Google Classroom where we can get together as a class and talk about the AP exam as a whole. Ultimately, as we move ahead, we do need to practice some problems related to the open-ended type questions that will be on the AP exam. Once we get beyond the AP exam, I do have some other topics that I would like to cover with you related to some of the things that we did skip and were removed from the exam itself. They will not be removed from life and from future courses you take in college and beyond. That when they see physics on a transcript, they're going to expect that you do have some understanding of waves. And so we'll take a look at that as well. Those topics will be graded in the pass-fail manner that we're doing with these assignments, but you're going to want to do them. And then we'll also talk about your end of the year project as well, which will be due in early June. So as we move ahead, please look for some notification about getting together later in the week and talking about the AP exams. And again, if you have any questions, please let me know. I hope everyone is doing well. I do miss spending time with you, and hopefully we will have an opportunity to talk about everything we've learned here in person sometime as we move ahead with physics and with school as a whole. Hope everyone is doing well again, and let's get started. So our last topic is on energy. Now, gravitational potential energy is affected by our concept of universal gravitation. So to start off, when we take a look at this topic, we are going to have to remember what gravitational potential energy is. Gravitational potential energy was the concept related to the energy that's stored. Storage is a key part of this. Stored by an object based on its height or position. And so we said if we had the Earth and we had an object and we lifted that object above the Earth, that object had a certain height, and that height gave it the potential to fall back down to the Earth. And as it was falling back down, the potential energy was converted into kinetic energy. Now we're going to do some mathematical trick here that is going to be tricky for some of you, and you may need to go back and look at this video a few times to fully understand what it is I'm about to say. This is not a hard concept, but it is a transformation that allows us to take this concept of gravitational potential energy from the world we live in to the world of the universe, a much larger perspective. So imagine that this ball here that I have is lifted up to a height of 5 meters. And I drop that ball and I ask you what the change in potential energy is when it is at a height of 3 meters. Most of you would say that the change in gravitational potential energy is equal to mgh final minus mgh initial. From there, you would be correct in saying that the change in gravitational potential energy was equal to, let's give this thing a mass. Let's say that the mass of our object is 2 kilograms. And for the sake of argument, let's say that gravity is equal to 10 meters per second squared. And so gravitational potential energy here would be something like 2 times 10 times the final height of 3 minus the initial height of 5, and you would say that there was a change in gravitational potential energy of negative 40 joules, that the object lost 40 joules, and that 40 joules went into kinetic energy, for example. You'd be correct. Now, when we're talking about the universe, the Earth is an important place to us, but it is not an important place compared to other planets. Other planets have an equal right to be the center of the universe, and we have made that argument about the fact that the Earth is not actually the center of the universe, and the Sun is not actually the center of the universe, and our Milky Way galaxy is not the center of the universe. But any object could be considered the ground state for a gravitational potential energy problem. And when I say ground state, I mean where the gravitational potential energy becomes zero. So what we do in this type of a problem is we flip the problem over. And so instead of saying that the 0 point is the Earth, we say the 0 point is at a position of infinity, as far away from the Earth as you could potentially go. And you're going to say, well, wait a minute, that doesn't make any sense. That means that on Earth's surface, you have if you're going from an infinite far place of 0, when you get to here, which is infinity from that place, you would have an energy that was infinitely large. And you would be correct that the Earth's surface would have an infinitely large amount of energy relative to an object pulled from infinity to here. And so we make an adjustment in our equation by putting a negative sign in it. And so this is what this looks like. Imagine that the Earth was at an infinity from our 0 point. Our 0 point being way out in space. And so now we have flipped our numbers around. Now, to stick to the problem we just had, let's just imagine that instead of 5 being the high point, 3 is the high point, 3 meters, and this is 5 meters. So we have flipped our directions. And obviously, as we go down, we're getting bigger and bigger and bigger until we get to infinity, which is at Earth's surface. So the change in potential energy equation is going to have one little adjustment to it. The gravitational potential energy is going to be equal to negative mgh final minus mgh initial. And so that means we would end up here with the change of gravitational potential energy equaling would be equaling negative 2 times 10 times, now the final, if the object starts up high and drops down towards 5. So the final is 5 and the initial is 3. And now when we solve this problem, we get, because of this negative sign, the same change in energy that we got up here. And so what we're going to do is we're going to change our reference. And our reference is going to be changing from infinity being the infinity position having infinity amount of energy to infinity position having 0 energy and the Earth's surface having the infinite amount of energy. And so we're flipping our equation. Now you say, why do we do that? Well, that's, again, going to allow us to look at the change in energy. And that's really the key in this whole thing, that it's about change. It's not about the energy at any given point. That is irrelevant. We don't actually know the energy. We care about the change in energy that objects have. We know the effect of change is work, and work is talking to us about energy being converted from one form into another. So with this, we know that the gravitational potential energy is equal to mgh. And we learned in the last lecture, the last video, or one of the last videos, that g was equal to big G, the mass of the planet, divided by the radius squared. So we could substitute this in here and say that it is going to be the mass of the object times big G times the mass of the planet times the radius of the planet squared times the height the object is above the surface. We need to make an adjustment here because when we have been talking about height, again, we're always talking about this change in height. And so the height we've been talking about is the height above the surface. And so we are really looking at an equation where the height is going to be the radius of the planet plus the altitude. And since that is going to be equal to what we're going to call the radius, ultimately the height and r are going to be the same thing. And so this h is going to be converted to r, and then it'll cancel the square, and we get a new gravitational potential energy equation of the mass of the object times the mass of the planet, all of this with the big G in front of it, over r. And with what we learned in our previous concept, we are going to put a negative sign here to flip the reference point from the center of the Earth or the center of the planet to infinity. And so we have this new equation, and that is the equation you see here in our energy. The zero reference level has moved off to infinity. And so when we do a problem, again, it's about the change. We don't care really where infinity is. If we are infinity plus 10 meters from an object, and then the object moves to an infinity plus 5, the object has moved 5 meters. I don't care about the infinity. I care about the change. How far did it change? And so that is going to be calculated. To reiterate something I said here, when we are talking about r, we are talking about the radius of the planet, plus the altitude, radius of the planet plus the altitude gives us the total radius, which is going to end up in here. And it's going to be the change in those things that matters. Again, the negative sign. That negative sign is going to play into the next topic we're going to talk about, which is called escape velocity. And the escape velocity, and these are all in your notes. Before I go any further, this is a graphical representation of what we were talking about with the potential energy. This is called a gravity well, where we treat the energy as a negative. If this is our 0 point, this is a negative value down here. And so what we realize when we are talking about this concept of energy is that as we move up, we are gaining energy. As we're moving away from the planet, we are gaining energy. Even though we're getting closer to 0, if we're at negative, and we are, in our equation is negative G times the mass of the planet times the mass of the object divided by the radius squared. So it's the negative is we're moving up. We are gaining. We're going from negative 100 to negative 70 to negative 50. That's a gain in energy, even though it's in the negative to less negative. And when our old form, we were still gaining energy. In our old form, if we said the Earth's surface was 0 and the height was 5, we went from 0 to 1 to 2 to 3 to 4. We're gaining energy. So in both cases, we're gaining energy. It's just where infinity is, where 0 is. And so this is the negative infinity well. So next topic was escape velocity. In the notes, as I was mentioning, we'll start with a very basic concept, which is that the amount of energy we start with has to equal the amount of energy we end with. And so the kinetic energy we start with plus the gravitational energy we start with has to equal the kinetic energy we end with plus the gravitational energy we end with. Now, our objective is to take an object from the Earth and shoot it up so that it goes to an infinite distance from the Earth, that it doesn't return. And so remember what we said about infinity. We're now going to say that infinity, the infinity position, is going to have zero potential energy. It's going to be the 0 point. And so that means if we start on Earth's surface and we go up, the gravitational potential energy is going to go to 0. It's going to start at a very high value and head to 0. Likewise, if we are doing this problem, we want to figure out the exact amount of energy we need to get the object to go to infinity. We want the object to arrive at infinity with no extra kinetic energy. The object starts off, we shoot it at some velocity, we fire it off at some velocity, and as it's going up in elevation, it is going to be losing energy from kinetic, and it's going to be gaining it into the potential. It's going to be turning that negative potential into a potential closer and closer and closer to 0. And so when an object is rising up in the in altitude away from the Earth, we want it to be dropping the kinetic energy, and when it arrives at infinity, it falls over the infinity line and has no more kinetic energy. If it still has kinetic energy when it arrives at infinity, then we gave it too much energy to start with. So we want kinetic energy and the n to equal 0. So we have a constant. We know that the amount of kinetic energy we start with plus the gravitational potential energy we start with has to add up to a big old 0. And so 1/2 mv squared plus negative, this is how that equation works now, big G, the mass of the planet times the mass of our object all over the radius squared has to equal 0. And the mass of kinetic energy is the mass of the object as well. So putting that together, we get 1/2 mv squared is equal to big G, mass of the planet, mass of the object, divided by the radius squared. The masses of the objects are going to immediately cancel out on this thing. And this whole equation is going to simplify back down to be something like V is equal to 2 times the gravitational constant times the mass of the planet divided by and I made a mistake here because r and r squared cancel out. This should not, let me go back and be clear here, this should not have been r squared. Because I was getting to here, I was going, there's a glitch there. So let's be cautious on that. And so we end up with 2 gravity mass of the planet divided by r. And so we have and we take the square root. We got v squared, we took the square root. And so we now have a clean equation, and this is called the escape velocity equation. This equation, you do not need to memorize. It's not something that will be on an exam, the AP exam or anything like that. But it is something that you should know the impact of because it is very important. What this does is it tells us how fast we need to be shooting an object so that it will escape a planet's gravity. This is the equation that tells us how fast we need to shoot a rocket to get it off the Earth and get it to the moon. This is how fast we need to shoot an object from the moon and get it to come back to the Earth. The catch, though, is this would be without providing any additional energy. So if I have a rocket and I were to take a big, gigantic nug and put the rocket in the nug, here, let's draw a nug here. This is a big, gigantic cannon nug. And in here is my rocket. And I want to shoot it off so that there's no additional propulsion once it's fired out. Then I have to shoot at a certain velocity. This velocity would be extremely high. There would be a great amount of acceleration. No human could withstand this type of these type of forces. So what we have to do is we have to do a slow burn. If you've ever seen a rocket go up, you know that there is a there's flames and energy coming out for an extended period of time. And so instead of giving it all of its energy at once, which is what this escape velocity would be. It would be the initial kinetic energy to have it escape. We give it energy gradually to allow it to rise up further and further and further. Ultimately, with this escape velocity, we can work our way backwards and say, okay, well, we don't want to have that velocity. So how long do we have to burn our engines so that our rocket can go up and get out of Earth's gravitational pull to the extent we can leave Earth? As I mentioned to you, there is always a little bit of gravitational potential energy that is going to be between an object and Earth, because there's always going to be gravity. Every star in the universe is pulling on you right now, and you are pulling on every star in the universe. It's just we're so far from them, the amount is negligible for most. So something to think about. Again, if you have any questions, let me know. The escape velocity equation is here. To escape from Earth's atmosphere, you would need to be going, if you plug in the numbers, the mass of the Earth and the radius of the Earth at sea level, you'd have to be going about 11.2 kilometers per second to escape the Earth. And you could see that as you go up in altitude, that would decrease. Different planets have different escape velocities because they have different masses, they have different radii, and so you can see here how this all works out. If anybody has any questions, don't hesitate to ask. Congratulations on reaching the end of mechanics, and we will move into waves and some other topics after the AP exam.